All right, let's work on work kinetic energy theorem. So work kinetic energy theorem connects those two things, the work net and kinetic energy, or specifically change in kinetic energy. As any change in anything, we always find as final minus initial. So in our case, it's kinetic energy final minus kinetic energy initial. And kinetic energy is the energy that is connected with motion, and the formula for it is mv squared over 2. So the important thing to know is that if net work is 0, then there is absolutely no change in kinetic energy. So the object does not speed up, the object does not slow down. It might be changing direction, but keeping the same speed. And if it keeps the same speed, then the value of v doesn't change, and there is no change in kinetic energy. If net work is positive, that means that our object will end up with more kinetic energy, therefore velocity will be greater, speed will be greater specifically. So if net work is positive, then our object speeds up. If net work is negative, then our object is slowing down. So you will see both examples in our following problems. I'm using the same examples that I used in the previous video, so they should be familiar if you watched it. So let's start with force and velocity being in the same direction. Let's say that our object has a 5 kilogram mass. The force applied to it is 10 newtons, and it travels 3 meters to the right. It starts from rest, therefore initial kinetic energy is going to be 0 because velocity initial is 0. So work net, force distance cosine of 0, since they're in the same direction. 10 times 3 equals 30 joules. And then we write out work kinetic energy theorem. Work net equals change in kinetic energy, and since it starts from 0, then I can just forget initial kinetic energy because it's 0 and not write it down altogether in my big equation here. So velocity is what I'm looking for. So I'm going to rearrange this formula. I'm going to multiply both sides by 2, divided by mass, and then square root. So under the radical, I end up with 2 times 30, which was the work, over 5. And that gives me square root of 12, because 30 over 5 is 6, 2 times 6 is 12. Or I can rearrange it as 4 times 3, square root of 4 is 2, and then I can write it as 2 times square root of 3. If you plug it into the calculator, it's fine as well. So example 2, now my force is in the opposite direction. So in this case, some other force must have set our object in motion. So the object is sliding, and there's an opposing force. Maybe it's friction, maybe it's air resistance, or maybe somebody is hanging onto that box trying to stop it. Who knows? So the mass of the box is 5 kilograms. Let's say initial velocity was 10 meters per second, and then the force of 7 newtons starts acting on it and acts on it over 2 meters. What's the V final? Again, work net is the only work of this force, because that's the only force here. So force times distance times cosine of 180 gives us negative 14 joules. Then I'm setting that net work equals change in kinetic energy. Our initial kinetic energy is no longer 0 because we start with 10 meters per second, so it's 5 over 10, because 5 is mass, 10 is velocity. And final kinetic energy, we're looking for V final. So we don't know what final kinetic energy is yet. But if I rearrange this, I will have negative 14 on the right. This will give me basically, this is 100, 500, 250. But in order to get rid of this 2, I will just go ahead and multiply everything by 2. So negative 14 turns into negative 28. This becomes 500, and since it was with a minus on this side, it will be with a plus when I drag it to the left of the equation mark, or equation sign, equal sign. So negative 28 plus 500 is 472. Then I divide by mass and square root and end up with 9.7 meters per second. Example 3, again the old example of force at 30 degrees to the horizontal, so it makes a 30-degree angle with velocity. Let's say mass is 3 kilograms, force is 15 newtons, initial velocity is 2 meters per second, and the distance is 1 meter. We're looking for V final. So force distance cosine of 30 gives us 43.3. Work net equals change in kinetic energy, so I'm setting 43.3 equal to 3 mass, V final squared, I don't know, I'm looking for it, over 2, minus 3 times 2.
It's 12 hours.
Thank you, because it's initial velocity is 2. So I will not multiply by 2. I'll just divide it because I know the masses and it's easy. So 43.3 plus 6, because this is 3 times 2 with a minus drag on the other side gets 6, equals 3 over 2 is 1.5, so 1.5 v final squared equals 43.3 plus 6. 43.3 plus 6 is 49.3. Divide by 1.5 square root gives me 5.73 meters per second. Now let's check. Work done was positive. And if work net is positive, that means that my object is going to be moving faster. And then if I can compare v initial of 2 meters per second to my final, which is 573, it holds. So we did it right. Example 4. Let's say the object starts from rest, slides down a 5-meter incline. What is the speed with which it ends its motion? In other words, what's the speed at the bottom of the incline? So the force acting on the object is force of gravity, which is mg, so 2 times 10 is 20, distance is 5, cosine of 60 gives me 50 joules. Then I said that 50 joules equal to change in kinetic energy. Since the object starts at rest, this becomes 0, so 2 for mass, v final squared over 2 equals 50. This cancels, so I end up with v final squared equals 50, so square root that gives me 7.1 meters per second. Again, work is positive, the object ends up moving faster than it started, which was rest, so everything works out fine. In the next example, the object is sliding upwards, so that tells you that there was some initial force. Maybe it was somebody's hand, maybe it was a spring, something set that block in motion up the incline. So work of gravity in this case is negative 50 joules. And let's say initial velocity was 11 meters per second. What's the v final? So negative 50 is work equals change in kinetic energy here. And negative 50 equals 2 over 2 times v final squared. Initial velocity is 11, so I'm setting it equal to 11. I'm plugging 11 into the formula. So, and then I'm going to divide by 2, both sides. So v final squared equals, this gives me 121, 50 minus, positive 121 minus 50 is 71. So then my v final is just the square root of 71, which is a little more than 8. Because 8 was 64. So 8.4 meters per second is your v final. Is it faster or slower? Well, analyze. Work net was negative. Therefore, you have to end up with an object moving slower than it started. It started at 11, ends up moving at 8.4. The physics is correct, and so is your math. Example 6. I have 3 forces acting on the object. So what I'm going to do, I'm going to find net force first, and then use the net work done by that force in the formula. This was in the previous example, so I'm not going to explain it again. I'm just going to use the same numbers. So our net work equaled 32.7, and then I'm going to set that equal to the change in kinetic energy. If the object started from rest, then 32.7 is simply v final squared, mv final squared over 2, which is final kinetic energy. So rearrange again, multiply by 2, divide by mass. 65.4. And then if mass was 2 kilograms, I was supposed to divide it by 2. Mess up! Oh boy. So let me recalculate it real quick. Teachers do make mistakes. 65.4 divided by 2 square root. It should have been 5.71 instead of 8.1. I am really sorry, but as far as physics goes, either it's 8.1, which is incorrect, or 5.7. It's still greater than initial, so that works out. So your net work was positive, and the object ends up moving faster than before. And this is it for